So section 5.6 is on inverses of functions. And first of all, I want you to tell me some observations. What are things that you noticed about a couple of those activities, a couple of the slides that you did? Anybody have any observations about these things? Well, these two functions that I've chosen to put together on the same screen, what are they? Opposites, yep. X squared and square root of x are opposites of each other, right? Okay, if I want to get rid of a squared, I square root it. If I want to get rid of a square root, I square it. Okay, so they're opposites of each other. Okay, another way of saying that is that they're inverse functions of each other. Back when we taught you Algebra 1, we asked you what's the opposite of addition, right? And you all said subtraction, right? Okay, addition and subtraction are inverses of each other. Okay, and when we asked you what's the opposite of multiplication, you said division. Multiplication and division are inverses of each other. So squares and square roots are inverses of each other. Make sense? Okay. Then I asked you to fill out this table for me. Okay, you all did an amazing job on that. I had some numbers for x, -3, -2, -1, 0, 1, 2, and 3. And what did you do to generate this table on the right? Yeah, we squared the x. -3 squared is 9. -2 squared is 4. -1 squared is 1. Okay? So we got this parabola. We only had a few points compared to all the points that are possible out there, but we're dealing with nice round, even, whole numbers, not even, but whole numbers. And they have the ability to put all the decimals, fractions, and everything else in there. Okay? Then I asked you to pick some nice numbers for this function, square root of x. So what are nice numbers that we might want to try in the square root of x? 1, because we know the square root of 1, right? Square root of 1 is, okay, what's another nice number? 4. Square root of 4 is 2. We don't want to try the square root of 3 because we don't know that off the top of our head, right? Okay, we tried 9 and got 3 out. We put 16 in for our input, and our output is 4. When 16 goes in for x, y, or the function, becomes 4. Okay, and we got this half parabola that opens to the right. Make sense? So what do you notice about the tables? They're not the same size, are they? One's much longer than the other, much bigger. But what do you notice about the data that's in the tables? Then, yeah, it's the same. It's just that it's flipped, isn't it? We see 0. If we took the square root of 0, we'd get 0. We see 1 and 1. We see 2, 4. What is it over here? 4, 2. We see 3, 9. What is it over here? 9, 3. If we put in 4 for this and squared 4, we'd get 16. What is it over here? 16, 4. Okay. So if I give you something like this, I didn't ask you to do the other half of this, the inverse function of this one. Okay. But I asked you to figure out what's the equation that would go through these points. And you did a great job with it. Right? I looked through the slides. I think almost everyone got this particular equation. Okay? Because we ask ourselves, if I put in -8 and get out 2, and I put in -1 and get out -1, I put in 0 and I get out 0. We tried some linear things that didn't work. We tried adding things and dividing things and so on. We finally realized that this is the cube root of x. Okay? So if I wanted to graph this guy's inverse, and I had this table, what would I do to make that happen? What did Ben notice about the inverse tables just a moment ago? What did he notice about these guys? The x's and y's are just what? Flipped. Okay? So if I wanted to find the inverse and I have these points, what would I need to do? Flip them. Okay? So Jordan, would you read the y's for me? I'll put them in the x's column. Okay? And Kayla, would you read the x's for me? I'll put them in the y's column. Very good. So if I wanted to graph the inverse of the cube root of x, I'm just going to switch the points around. I will have a point at -2, -8, 2 back, 8 down. I'll have a point at -1, -1, 1 back, and notice my scale is by 2s, so I only have to go halfway between. So -1, -1. I'll have a point at 0, 0. I'll have a point at 1, 1. And I'll have a point at 2, 8. From the other day when we did a Desmos activity, didn't do a very good job of drawing that. Does anybody remember what that function was? Parabolas are U-shaped, right? What makes this little inflection point in the middle and makes it go up and down on one on the right, up on the right and down on the left? This was cube root, so that's going to be cubed. And what is the relationship between the cube root of x and x cubed? Opposites. They're opposites. They're inverses. Okay? So on your sheet, switch them up. Okay? If I have a function on the left and I want to know its inverse on the right, what will you do? Very nice. So fill that out for me. job. Thank you. All right, what did Tyler do? Flipped it, okay? He took the x's and put them in the y's column. He put the y's in the x's column, okay? So you can do the same thing in the one on the right, can't you? The one that's your homework problem, okay? Let's look at this and see what it looks like, okay? The red are the original points. So we have these points marching along like ants up the wall, okay? And then the green are the ones that Tyler just put in. And I put a nice little dotted line across here so that you could see the relationship between them. What's going on with them? If you look at a graph and you need to decide if two functions are inverses of each other or not, what are you looking for? Slope. So what would our slope be here? How much are we rising and how much are we running on the red dots? What's our change in y? -7 minus a -4 is how much? Okay, so our rise is 3, our run is 1. Okay, what's going on with these guys? What's the change in y here? -3 minus a -2? Minus a minus is plus, right? So -3 plus 2? What's the change in y here, or change in x here? -7 minus a -4? Okay, we have a slope of 3 over 1 here. Our slope here is -1 over 3. Actually positive 1 over 3, right? Because -7 minus a -4 is -3. So one has a slope of a positive 3. The other has a slope of 1/3. Notice that they're both rising, right? Rise over run. They're both rising as we go to the right, just that one's a lot steeper than the other. Okay? This is our reflection line, isn't it? We saw reflection lines when we worked with parabolas. And we had a line of symmetry that we graphed. Made our graphing a lot easier because we only had to graph half as many points. Okay, same idea here. This is the line y equals x. So if you switch your x and your y around, wouldn't it make sense that they're going to be equal distance away from that line y equals x? Hopefully. Okay. So you've got a problem just like that, like this, on your assignment, on the right-hand side of your sheet. But I do want you to graph it. Okay, so you're going to graph those points as well. Connect the dots for each table. Okay. All right. Yeah, the table is actually there. The original function has a list of x's and y's. So they're going to graph those points. Yep. And then they're going to find the inverse by flipping the x's and y's in the table and then graph those points. Okay. All right. So now that we understand the idea of doing it with finding an inverse when we have points in a table, how are we going to find the inverse of an equation. And this equation's in functional form. F of x equals 3x plus 2 is just a grown-up way of saying y equals 3x plus 2. Okay? So y equals 3x plus 2. Does anyone have any idea how we might find the inverse of that function? Oh, I'm sorry. Absolutely. What do you think it might be? Very good. Very good. Awesome. So yes, let's just flip it. Make them opposites, right? If this is y right now, it's going to be an x. And if this is x right now, it will be a y, won't it? Okay. So the first step on these problems is to rewrite it with a y in its spot. Okay. Then the second step is to switch the x and y around. Make the y be an x, make the x be a y. Make sense? Because we're switching the data in the table, right? Same process here. Now, when we graph something like this, we're used to graphing it because it's in slope-intercept form, right? Y equals mx plus b. What's my graph, or which one's my m and which one's my b? M is 3, yep, and b is 2. Okay, so if I'm graphing that guy, I could put a whole bunch of points in there, try a whole bunch of numbers, make a table, but you guys know the shortcut, right? We begin at 2. 2 on the x-axis or y-axis? Y-axis. When x is 0, y is 2. And then what do we do with that guy? Up 3 over 1, because our understood slope is 3 over 1. So we're going up 3 over 1, up 3 over 1. And then we draw our line. I went over 2, didn't I? Helps if I graph it right. Up 3, harder to do when there's the scale factor's different. And then up 3 over 1. There we go. So watch for my down 3 over 1. Get a nice straight line for you. Okay? All right. Now, we have the inverse here, but it's not in a form that we can use yet, is it? Can you look at that and decide how to graph it? Nope. So what do we need to do to this blue equation, the inverse, in order to get it into a place where we can graph it? Why is this one easy to graph? Everybody's asleep on Monday. It's in what form? Slope-intercept. How do we get this guy into slope-intercept? How do we get this into y equals mx plus b form? You guys know. Christian, how do I get it into y equals mx plus b form? We want it to look like the original, don't we? But we had to switch the x's and y's to get the inverse, right? So how can we get it to look like the original? Yeah, we don't need a 3y, we want a 1y, don't we? And we don't want a 2 hanging out with it. We want that to be on the other side, don't we? Okay. So the reason this is powerful is the y is all by itself. So what can we do to get the y by itself? Divide by 3, right? But before we divide by 3, because remember we have to divide everybody by 3, it would be nice if the 2 was on the other side first, right? But you could divide by 3, it wouldn't hurt anything. Just have to deal with the fraction beforehand, earlier than you would otherwise. Okay? So we can take the 2 to the other side and get x minus 2 is equal to 3y. And then divide by 3, because we want just a single y, not 3 times y. But let's divide every single term by 3. And most people like to have the y on the left-hand side, right? It's not absolutely necessary, but you can leave it on the right-hand side. Most people prefer to write this on the left-hand side. So if I switch them around, x is going to be divided by 3. That's 1/3 times x, right? Why do I like to have 1/3 times x? That's my slope, right? Okay. And then I'm going to have a minus 2/3. Okay. This one's not as easy to graph, is it? Because we've got a fraction. So we're going to start. Our beginning is a minus 2/3. Our b is minus 2/3 on the y-axis. So minus 2/3 is almost to -1, but not quite there. Okay. This time my slope is what? 1/3. So I'm going to rise 1 and run 3. Okay. So I was at 2/3. I was almost to -1. When I rise 1, I'll be almost to 0. But then I have to run 3. So each of mine are by 2s. So 1, 2, 3. I'll be right there for my second point. Okay. Do the same thing again. I'm going to rise 1. So I'll be almost to 1. And then I'm going to run 3. So this is a good review of, not doing a good job of drawing a straight line there, a good review of some of the things that we've been talking about this semester: graphing lines, graphing parabolas, graphing radicals, we've graphed absolute values, and so on. Okay. Do those two look like mirror images of each other? Most lines do, don't they? But inverses have to be mirror images across the line y equals x. Okay, they should open up evenly across that line. All right, so far so good? All right, you've got one just like it on your assignment sheet. Okay, next one. So that's what it looks like. And here we go. So how are these functions related? They're a third power and a cube root, right? So we suspect that they're going to be inverses of each other. We look at them across the line y equals x. Are they mirror images of each other? Everybody should be nodding their heads and saying, yes, they are. Yes. Okay. Now look at those equations though. They're slightly changed up, aren't they? They're not just a cube root of x and a x cubed, are they? Y, I should do this one in red since it matches my color scheme going on here. Y equals the cube root of x plus 2 minus 1, and y equals x plus 1 cubed minus 2 are inverses of each other. Okay? Easy to tell by the graph, right? What do you notice about these things, these equations? Other than that they're inverses, let's look at the numbers themselves. Positive 2 was with x underneath the radical. Where's it at now? Outside the radical, or outside of the parent function, the parentheses, right? And opposite sign, isn't it? Negative 1 was outside of the radical, shifting it which way? Down 1. Now it's in the parentheses, and it's shifting it left 1, right? Correct? Okay. Okay, so let's see how these work. First of all, for something to be an inverse, or to be a function, we learned something a long time ago, I think. But my pre-calc stuff is blending in with my algebra too. Does anybody remember something called a vertical line test? No? Yes? Okay. Probably haven't used it. Okay, a vertical line test says, right. Okay, so if it's squared, x is squared, it's not going to pass the, it's okay, right? But when we take a square root, have a positive and negative square root, then it's not going to pass it. So what we can do is we can say, hey, is there any place, anywhere on this graph where we can draw a vertical line and hit the red one in two places? We can't, can we? Okay, was there any place along this where I can draw a vertical line and hit the blue line in exactly two places? Or more than two places, more than one place? There's not, is there? So both are functions. Okay? We can touch it once, okay? But let's look at this. Could we draw a vertical line somewhere and touch that graph in more than one place? Lots of them, right? So I could go here and touch it in two places. I can intersect it here in two places with this line. I can intersect it here in two places with this line. So these are functions. This is not a function. Does that make sense? Definition of a function says that for every x, there's exactly one y. Notice that for this value of x, there are two y's. So it doesn't pass the function test, the vertical line test. Okay? So far, so good? All right. So they ask if the inverse of g of x is a function, and if so, they want us to find its inverse. Okay? So, first of all, cubics. Tell me in general, what does the cubed, x cubed graph look like? From last week, I think it was, when we did this exploration. What does x squared look like? Everybody show me with a gesture. Okay, right? X squared, touchdown, right? Or Hulk if it's negative, right? What does x cubed look like? John Travolta, okay? Rising on the right, falling on the left, or rising on the left and falling on the right, depending on whether the A is positive or negative, okay? Saturday Night Fever, okay? So is that going to be a function? Yeah. Anything that's like that is not going to have a problem, okay? So we will have a function when we find its inverse because it's a function and not something that you could send a horizontal line through and cross in two places. Its inverse will be a function. We'll talk about horizontal line tests in just a second. Okay, so first step in finding an inverse. We didn't write it down, but we should have. First step in writing an inverse, if it's a function, we change it to what? A y. Yep. So change the function notation or g of x. Change the function notation to y. Okay. So we don't have g of x now. We're going to have y equals 3x cubed minus 2. Next step. What do we have to do next? Switch the x and y. So now my new equation will be x equals 3y cubed minus 2. And then what's the last step? Get the y by itself. If this one won't be in slope form because it's cubed and so forth, but to solve for y, yes, get the y by itself, okay? Okay, so if I want to take x equals 3y cubed minus 2 and solve it for y, what's the first thing I have to do to start to get that y by itself? Bring the 2 over, okay? So I had x equals 3y cubed minus 2. I'm adding 2 to both sides. So x plus 2 is now equal to 3y cubed. That is looking better already. What's the next thing I have to do to get the y all by itself? I want a cube root, right? But do we need to divide by 3 first? Does that make sense to everybody? We might want to get the 3 away rather than try to cube root it with the y. So we're going to divide it by 3. That means divide the whole left side by 3. Okay? And you can split it out. You can call it x over 3 plus 2/3. That would be okay. You can leave it as a whole fraction. That's okay too. Nope, it'll probably be, yep, it'll probably be all under the radical. Okay. And then we're going to get the y cubed by itself. It's already by itself now. And we've got this x plus 2 all over 3. But it's a y cubed and we want it to be a single y. So what are we going to do? Thank you. Cube root it. Opposite of cubed is cube root. Take a cube root of both sides. And then we're going to get y equals the cube root of x plus 2 over 3. Now, some would argue that we've got a radical in the denominator, don't we? that's a pre-calculus issue. For algebra 2, we're okay to leave that radical in the denominator since it's the whole thing that's a cube root. Does that make sense? You don't have to rationalize the denominator when it's like this. Okay? All right. So we've got another one just like this on number 4. Okay? Here's that sideways parabola. Okay? It's actually two functions put together, okay, to make something that is not a function. Okay? Remember when we did this, when we found this guy? What is this, the top part? What would make this graph? Not cube root, you're close. Square root of x, okay? This is a square root of x as its parent function, but it looks like it's shifted to me. Where is it shifted? Two to the right and three up, okay? So this is a square root that is 2 to the right and 3 up. How do I make it go 2 to the right? Negative under there, so minus 2. How do I make it go 3 up? Plus 3. Okay? So there's our square root function. And then this is the same thing, only it's the y equals the negative square root of x minus 2 plus 3. Flips it. Okay? So this guy is not a function because it's two separate equations put together, and it doesn't pass the vertical line test. Okay? When you're thinking about a function and whether its inverse will be a function or not, you can look at something called a horizontal line test. Does this pass a horizontal line test? For every horizontal line that you draw, will you only touch it in one spot? Yes. So its inverse is a function. Okay? So if I want to find the inverse of y equals the square root of x minus 2 plus a 3, what do I have to do? First step's done. It's not in function f of x or g of x notation, right? What's the second step? Switch them, right? Okay. So it will now be x equals square root of y minus 2 plus 3. So far, so good? What's the next step of finding an inverse? Bring the 3 over, solve for y. Get the y by itself, so we have to take away a 3 from both sides. X minus 3, square root of y minus 2. What's the next step, Kobe? Square both sides. Very good. We want to get rid of the square root. The opposite or inverse of square root is squaring. So we square both sides. What are we going to get here, Macy? This is the tough one, right? So we want to make sure we don't just square the first and the last. So what do I have to do to find the answer to this side? What do you think we might have to do? No, I've seen you do them. Well, x minus 3 is squared, right? What does squaring mean? Take it times itself. Yep. So we need to take that x minus 3 times itself, don't we? And I didn't write that very well because I was talking while I was writing. Okay. So when we take x minus 3 times x minus 3, what are we going to get for our first term, Jordan? Very good. What are we going to get for our outside, Sarah? But positive 3x or negative? Positive x times negative. Yep. Okay. What are we going to get for our next term, Caitlin? Last term is going to be a positive 9. And what are we going to get for the middle? Negative 3 times an x is going to get us ooh, even better. I like that. Yes, 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 yes. Let's do that. Let's leave that in vertex form. I'll show you two ways. So this was x squared minus 6x plus 9, but then we're going to do the taking the 2 to the other side. So it's better, especially when we're graphing. Took you down a rabbit hole. Sorry about that, guys. Let's just leave this as x minus 2, 3 squared equals, when we square this, we just get a y minus 2. Okay? What's the last step then? So plus 2. We're going to add 2 to both sides. As long as we recognize that we can't just take negative 3 and a positive 2 and add them up, we're perfectly fine to leave that as x minus 3 squared plus 2 is equal to our y. And most people like to put the y on the left-hand side. Yep. So if I want to graph this, this is an x squared shifted where? Right 3, and so we go right 3 up 2. There's our vertex. A is 1, so it's not changing it, making it, stretching it out or anything. So when you move 1 to the right, you only have to move 1 up, or 1 to the left, move 1 up. And if you move 2 to the right, 2 squared is 4, we would be 4 up. 2 to the left is going to be 4 up as well. And there's our new parabola. Okay? So you've just got a few problems to work on your sheet.